Think of recharging your electric car in less time than it would take you to have a cup of coffee. Think of driving more than 900 miles without any fear of looking for a charger. Imagine a battery that does not catch fire, unlike those that made headlines for causing destruction last year. That era is no longer just the stuff of science fiction. In billion-dollar laboratories behind closed doors, and in some of the biggest names in automotive manufacturing industry, a race of technologies is on. It doesn't involve developing faster cars or better electric vehicles. It involves developing the best battery. Over the past few decades, it was the lithium-ion battery that has been responsible for taking over smartphones, laptops, and electric cars. These batteries made possible the emergence of companies like Tesla and made the automotive industry what it is today. However, no matter how revolutionary it has been, any technology sooner or later reaches its limit. Recharge takes too long. They are expensive. Extreme cold affects performance significantly, and despite all the progress being made, safety concerns are still posing challenges to the developers of these batteries. A whole new technology emerges right now. Solid-state batteries could provide solutions to almost all problems that are associated with using these devices in electric cars. In case of success, they won't just improve EVs. These batteries could completely redefine transportation of tomorrow and maybe determine who would be dominant in the next trillion-dollar industry. This is the story of the world's most important battery race. Why lithium-ion has gone as far as it can to comprehend the urgency of the quest for a new battery, we first need to comprehend the battery technology behind today's electric revolution. The lithium-ion battery was commercially produced in the early 1990s. From then on, these batteries powered billions of gadgets and virtually all contemporary electric vehicles. The lithium-ion technology exploits a simple concept. In these batteries, lithium ions move between two electrodes through a liquid electrolyte. That sounds elegant. But this liquid electrolyte is one of the battery's biggest weaknesses. It is very flammable. It can lead to a hazardous chain reaction called thermal runaway in case the battery is damaged, heated up, or not properly assembled. Even though these situations happen much less often than the total number of batteries used in the world, they are still a big engineering problem. Engineers have made great progress in developing better safety and cooling systems. Still, they are looking for chemistries that will help them make batteries safer and more efficient. There is another reason why lithium-ion batteries are problematic. These batteries are reaching their theoretical limits. Continuous small improvements are happening. But revolutionary improvements get harder. In order to achieve revolutionary range, charging speed, and safety, researchers believe that a completely different battery design is necessary. This is what the solid-state battery represents. The breakthrough called solid-state. What does make a solid-state battery stand out from the crowd? There is one element which makes the difference. In solid-state batteries, the liquid electrolyte is replaced by solid material, such as ceramic, sulfide, oxide, polymer, or some other solid electrolyte that can conduct lithium ions well. It looks like a simple engineering trick. In reality, it affects nearly all aspects of the battery performance. The solid electrolyte will make the battery safer because the risk of flammability will be eliminated and allow using lithium metal anodes instead of graphite, thus allowing the battery to store more energy in the same space. The resulting effect is an increase in the driving range of an electric car, reduction in battery size and weight. Also, solid-state batteries have the potential to be charged much faster and operate for a longer period of time. But reaching those properties in mass production is quite a challenging task for now. Certainly, there are barriers on the way. Mass production of solid-state batteries is hard, high costs, lack of durability and stability of the interfaces. But overcoming these barriers will not only bring profits to the winners. These companies will set the standards for the whole automotive industry around the world, and this race has already begun. While Tesla was scaling lithium-ion, Toyota was quietly building the largest patent wall in battery history. Since the late 2010s, the company has poured more than $15 billion into solid-state research and now holds over 1,300 patents in the space, more than any other company on the planet. Toyota's approach uses a sulfide-based solid electrolyte, chosen specifically because it can eventually be manufactured with equipment closer to what battery factories already use, rather than starting from a blank sheet of paper. The company claims its cells can charge from 10 to 80% in under 10 minutes and deliver more than 600 miles of range, numbers that would make Tesla's current lineup look a full technology generation behind. In February 2026, Toyota deepened its supply chain by partnering with Idemitsu to secure the specialized materials needed for next-generation cathodes. locking in the raw material side of the equation the way it once locked in hybrid patents in the 1990s. The stated target is small-scale production between 2027 and 2028. Toyota isn't trying to outmarket Tesla. It's trying to outpatent it and make sure that when solid-state batteries go mainstream, the licensing fees flow through Toyota. Tesla's biggest challenge yet. For more than a decade, Tesla has defined the modern electric vehicle industry. Its innovations in battery management, software integration, charging infrastructure, and large-scale manufacturing help transform EVs from niche products into mainstream transportation. Rather than focusing exclusively on solid-state batteries, Tesla has continued refining conventional lithium-ion technology. Through larger battery formats, improved cell chemistry, and manufacturing innovations such as dry electrode processes, the company aims to reduce costs while increasing efficiency. This strategy has delivered meaningful improvements without waiting for an entirely new battery architecture to mature. But what happens if a competitor successfully commercializes solid-state batteries first? Imagine an electric vehicle that offers substantially longer range, faster charging, and enhanced safety at a competitive price. Such a breakthrough could reshape consumer expectations across the industry. Tesla has repeatedly demonstrated its ability to adapt quickly, and the company continues to invest heavily in battery research. However, the transition to any new technology depends on technical feasibility, cost, and manufacturing readiness, not just laboratory performance. The question is no longer whether battery technology will evolve. It is who will commercialize the next major breakthrough first. Will Tesla extend its leadership? Or will a new generation of battery innovators redefine the future of electric mobility? The answer may determine the next chapter of the automotive industry. Who will control the battery supply chain? The battle over batteries extends far beyond chemistry. Even the most advanced battery cannot be built without a reliable supply of critical materials. Lithium, nickel, cobalt, graphite, manganese, and rare earth elements all play important roles across today's battery ecosystem. Although the exact mix varies by battery chemistry, countries rich in these resources have become strategically important, while governments are investing heavily in refining capacity, recycling technologies, and domestic manufacturing. China currently plays a dominant role in several parts of the global battery supply chain, from processing critical minerals to manufacturing battery components. Other regions, including the United States, Europe, Japan, South Korea, Australia, and Canada, are investing billions to diversify supply chains and strengthen energy security. Recycling is becoming another crucial piece of the puzzle. Recovering valuable materials from used batteries could reduce environmental impacts and lessen dependence on newly mined resources. The future of electric mobility won't be determined by battery chemistry alone. It will also depend on mining, logistics, geopolitics, recycling, and industrial policy. The companies that secure resilient supply chains may gain advantages just as important as those achieved through scientific breakthroughs. In the battery race, materials are becoming as valuable as the technology itself.